I'm going to show you how I figured out the dimensions for my cone. In fact, I didn't start out making a cone at all. My original idea was to use 4 mirrors and have the mirrors reflect the sunlight onto the bowl. And to do that, I first took a piece of cardboard and I taped some aluminum foil to it. I glued it at the top so it'd be nice and flat. Next, I need to figure out what angle to put the reflector at. So first I took my solar cooker and made it point directly at the sun using my sun finder. Then I set the reflector at some random angle. And what I found was the sunlight was being reflected to over here, which is useless, right? I want the sunlight to be reflected onto the bowl. So I gradually increased the angle, making it steeper and steeper and steeper, until finally I had the sunlight on the bowl. Now, if this was a mirror, that would have been fine, because a mirror is nice and flat. But my aluminum foil was just taped to the cardboard, so it was wrinkly. So actually, that wasn't very precise, and it turned out the sunlight wasn't being reflected over here. It was actually over here. And the way I found that out was by using a more precise technique. And that worked as follows. I took a square, which is a carpentry tool. You can use anything, a piece of cardboard or a piece of wood, as long as it has 2 edges that are at right angles to each other. What I then did was I put one edge of the square flat against the solar cooker. And I took the other edge and I lined it up with the top of the reflector. And then I looked at the distance that the square overlapped the solar cooker. So here it extends out by about 1 inch. If I want to look at this from the point of view of a beam of sunlight that's arriving directly at my solar cooker, then what I do is I line up my eye with the top of the reflector right here and with a point that's 1 inch away from the solar cooker right here. And that's what a beam of sunlight would see arriving at the top of my reflector. So I've set up my tripod right here. If you look at the top of the reflector right here, you can see what the beam of sunlight would see. The beam of sunlight would reflect off here and then would go to a point right about there. It's a little hard to tell. If I put my jar right there, you can see where the sunlight will hit the jar. So right here. But an easier way to do is to take a bright piece of, in this case a bright red piece of foam, put it against the reflector and just gradually pull it away. Right there. So that tells me that that's where the sunlight will arrive at my jar. So right about here. Which is not bad. It's not over the complete surface of the jar. And that's actually good enough. You don't need to figure out where a beam of sunlight would arrive here. Look at the perspective for a beam of sunlight arriving there, because any beam of sunlight arriving here will then hit the bowl right here and reflect onto the jar. So it's good enough just to know where the light will arrive at the top. But that also told me something else. Any beam of sunlight arriving right here is going to arrive at the bowl right here at about this angle. It's going to reflect off at around this angle, which will then go here and reflect off at about this angle and be lost. So that's almost useless. It's almost useless because the sunlight will be reflected off, but this is not a perfect reflector, so some of the sunlight will be turned into heat, and that heat will conduct through the bowl to the jar. But also a lot of that heat will just be lost to the surrounding air and to the back. So what I realize is that I don't want 4 reflectors at all. What I want is a whole bunch of reflectors that are the width of the jar. So basically I want a cone. So the next step was to figure out how many of these segments I'll need and how wide to make them, the dimensions. Now to figure all that out turns out to be quite easy. We know a lot of things. For example, we know that at the top here each segment is around 4 inches. We also know another thing. We know the radius of the circle made by the top of the cone. We know that because remember, if we look straight in at the top of the cone, we look at a point that's 1 inch away from the edge of the box. So we know the radius of the circle made by the top of the cone is a circle that has a radius that goes from 1 inch away from the box to the center of the bowl. So if we take our square once again and position this end at the center of the bowl, and we see that this end right here is 10 inches away from the center of the bowl. So the radius of the circle of the top of the cone is 10 inches. And while we're here, we see that the radius of the bowl itself is around 6.5 inches. Okay, so now we need to figure out what is the circumference of the circle at the top of the bowl, of the cone, or the length of the circle made by the top of the cone. And to do that, it's fairly simple geometry. The circumference or length of any circle is 2 times the radius times pi. So 2 times, we measured 10 inches, times pi, and that gives us 62.8 inches. So the circle made by the top of our cone is 62.8 inches around. So I'll just store that away. Now, we know that our segments are going to be 4 inches each at the top, or roughly 4 inches. We'll know what it really is in a minute. So we divide this by 4 inches. That tells us if we want 4-inch wide segments, and we know the length 62.8 inches around, there's going to be 15.7 of those all around. So in other words, we'll have one 4-inch segment, another one beside it, another one beside it, another one beside it, and there'll be 15.7 of them to make up the full circle, which is, we don't want 15.7, so we'll choose 16 instead. So let's get that length back again. 62.8 is the length of that circle, divided by 16 instead. And that tells us that our segments at the top shouldn't be 4 inches, they should be 3.9 inches wide. Okay, so the segments at the top here will each be 3.9 inches. Now, we know the radius of the bowl here, of the bottom of the cone here, which is the same as the bowl. And we know that it's 6.5 inches here. We measured that a minute ago. So, again, using our formula, we could find out what's the length of this circle right here. So, again, that was 2 times 6.5 is what we measured, times pi. That tells us, I'll store that away. That tells us that the length of this circle is 40.8 inches. We already know that we're going to have 16 segments. So if we divide that by 16, we get 2.5 inches. So now we know the dimensions of our segments. They're around 3.9 inches at the top, and they narrow down to about 2.5 inches at the bottom. So now we know everything we need. We know we need 16 segments, and we know the dimensions. The last thing we can do is figure out if the cone is really going to help us, and how much. We can do that by calculating how big a capture area we get with just the bowl versus with the cone. You can think of these capture areas as the holes that the sunlight has to travel through in order to enter the cooker. You don't get any more sunlight than will fit through these holes. To give a rough number, the amount of power arriving down here on Earth from the sun is around 100 watts per square foot. The capture area for the bowl is the circle made by the rim of the bowl. We already know the radius of the bowl is 6.5 inches. To get the area of the circle, the formula is the radius squared times pi, or the radius times itself and then times pi. So the area is 132 square inches. Next, we calculate the area of the circle made by the top of the cone. We already know the radius of the cone is 10 inches. Using the formula again, we multiply the radius by itself and then times pi to get 314 square inches. So finally, to find out how much more power the cone can possibly capture versus the bowl by itself, we simply divide the area of the cone's capture area, 314 square inches, by the bowl's capture area, 132 square inches. And we get 2.37, or roughly 2.5 times the capture area with the addition of the cone. So the cone will help. Notice that the bowl and cone shapes don't matter for this calculation. We're just talking about the amount of power we can potentially get from the sun. We say potentially because each time the light reflects inside our solar cooker, goes through glass, or is turned into heat at the cooking pot, we'll lose a little of that power. The glue I'm going to use is just this random glue that I picked up in the school set parts section in a drugstore. Nothing too fancy, randomly picked out, and there's some parts all ready to go there. I'm going to put the panels close together in their final position so that when they're unfolded they're right. But I still want to be able to fold it easily. And to do that, what I did was I put a 3-piece of duct tape on the front between the two panels. And then the next set of panels, I put the duct tape on the back. 1, 2, 3. That way, this set of panels will fold like this, and this set of panels will fold like this. So to do that, what I did first was I reinforced the each piece here along. Let's see where I start. Right here on the edge with a little bit of aluminum tape because it just needs to be reinforced. The aluminum foil glued to the cardboard I think would eventually, the duct tape wouldn't interact with it very well. It would pull off. So I reinforced by putting a piece of aluminum tape around it. Aluminum tape is just stuff you get at a hardware store. And so I did that along the edges in 3 places. I use duct tape because it has threads embedded in it, and so it'll handle lots of folding and unfolding. So here we go. I've noticed I've replaced the duct tape, not replaced the duct tape, sorry, I've covered the duct tape with aluminum tape wherever there was duct tape in front, for appearances mostly, but also just for heat resistance, I guess, too. There's not really going to be a lot of heat on the reflector anyway. I've also got ways of closing it up at the ends. I'll show you that in a minute. Now, to mount it and hold it in place on the box, I cut these slits right here and then reinforced the edges with duct tape. And then I made 4 of these shaped things, and they go inside here, and they're what the cone is going to be mounted on. So 4 of these, and to mount the cone on there, I've got slits in every 4th cone. 1, 2, 3, and the 4th one right there. And I've also reinforced the edges of these slits as well with tape. In this case, I'm just using clear packing tape, and I got tired of using aluminum tape. And what I'm doing underneath is, when I put it underneath, you can see that when you put it underneath, I just give them a little twist here, back and forth, and that holds it in place. A little S shape there. Ta-da! Okay, now the moment of truth. I think the way I'm going to do this is I'll first connect the 2 ends. So to connect the 2 ends, I simply put a piece of duct tape around to reinforce this again. A lot of reinforcing in this project. And then I made some holes, and then I put wire through the holes. There we go. I just stand this up so you can see it. There we go. And I just take the wires and twist them, and voila, that's closed. And we do the same for the bottom. So the idea is I slip that into here. There we go. And you can see on the inside it's right there, and I simply give this a little twist, It's held nicely in place. And now let's do the next one. Just up. Just one flaw in my devious plan. And you can see what it is from the front here. These parts here aren't supported, so they droop inwards. So I'm going to have to do a hack to fix it, and I found a hack. But if you're going to do a hack to fix something, make sure it's an elegant hack. So what I did is I took some piece of cardboard here, wrapped some aluminum tape around at least one side, and I simply wedged them between the bowl and the insulation. And there we go. Thanks for watching. Click here for Part 4. Part 4 covers the design and construction of the cooking table used to sit the jar on in the solar cooker. And if you missed seeing the solar cooker in action, click here for part 1.